No.
Oh my.
Okay. All right. Can you hear me? Good. Welcome back. You have good breaks? Decent breaks? Most of you at least? All right. Okay. So we're starting the... Anyone missing a screw? We're starting the next part of our course. We're going to be devoting a whole bunch of weeks from now on to basically one large topic, but we're going to get into it piece by piece. And so today I want to, I actually lied, by the way, a little bit. We're not completely done with our discussions of infinities. We'll get back to some other infinity issues today by the end of the class. To warm you back up, here's a definition you should all recognize. You've all seen tons of examples like this. Yes? Any questions? There's no tricks on the board. It's all completely self-evident. Great. What I'd like you to do for starters, just as a warm-up, introduce yourself to your neighbors and, well, hold on, I haven't told you what to do yet, other than that. Write a function that makes a copy of a tree. Think you could do that? Okay. So, function make, so copy tree, takes a B tree, and returns a B tree. Okay, go. Go. Makes a copy. There's always a way to Let go! Come on!
I don't know how you're passing, not passing the actual tree that's pointing to the memory. Because passing it by the actual
Dude, walk the tree and make a freaking copy. Come on. Alright, in 5, in 4, in 3, in 2, in 1. We're back. I didn't realize this problem was going to be such a wise-ass magnet, but apparently it is. Okay, so, B tree, 50. How many cases? 2. Okay. What do we produce? Yes? Otherwise it wouldn't be a copy, right? Okay, what do we do?
No. V. Copy tree.
Good. Okay. Alright. And we could write a check to make sure what? What's a good example here?
Copy tree leaf.
Copy tree of...
A tree.
Yeah, what should be?
A tree.
A tree? Yep.
Oh, yeah.
Okay. Okay. Yeah, kind of how copy tree should work. All right. Yes.
I feel like something that would be a useful check is to see if we store copy tree of a tree and then change it.
Yeah. So, well, we haven't talked about changing anything. We have no way of changing anything, so can't do that. Yeah.
Why can't we just return T?
Because I wanted you to make a copy of the tree.
Like you still are. Well, you still return a copy of the tree.
Will it? Will it now? Good. That's what I want to discuss today. Okay? All right. So, I'm going to move all this to the bottom. Okay. All right. So let me talk about another way to make the same tree. Okay. So let me call it the B tree. Let me do this. Okay? Alright. B node, sorry. So not okay, y'all should be. Okay, so here is A tree, and here is B tree. Okay? They look the same. And in fact, just in case you're worried that your eyes might be deceiving you, we can even tell Pirate to check it for us, right? So B tree is A tree, right? Basically check that they're the same. What do we expect? Check pass, check fail. Read very closely on the right to make sure that they look the same. Yes, ready? How many expected to pass? Any fail? Good. Okay, and it's going to pass. Okay? Good? All right. Now, it's patently clear that they're the same kind of tree, right? Both of them have a root that has the value 5. They have 2 children, right? A left child and a right child. And the left child has 4 at the root and no children. The right child has 4 at the root and no children, right? So it's patently clear that the same tree. And we printed them, they're the same. And we run them under Pirate. We even use the checking infrastructure of Pirate. And they come out to be the same. And yet, there's some sense in which maybe they're not quite the same. So let's draw a little picture here. So A tree is, make a node. Yes? Talk to your neighbors and tell me what picture you would draw for B tree. Go. 30 seconds.
Actually, 5 cows pointing to the trees and 5 nodes points to I think you might have like one both and pointing at it.
Okay. So, draw me the picture. Show me the picture. Show me the picture. Everyone, show me the picture. Yeah, okay, good. Okay, so basically what we have is we have node 5, 2 children, and this appears to be the picture. Right? Looking at the code, which thing is B node? Point at the board. B node. Everyone point. Up, down, left, right. Right about there? Up a little bit? Okay, right there. That's our B node, okay? So B node. Okay. That's A theory. Another possibility is that what's actually going on is B tree is this picture over here. We don't know because we don't quite know how the programming language operates. We don't know whether when we say in line 12, B tree is equal to node 5, B node, comma, B node. When we say B node, comma, B node, is that making a copy of the B node or not? Right? It's entirely possible. Look at the board for a moment. Look at lines 11 and 12. In particular, look at line 12. There's nothing right now that rules out the possibility that the picture that corresponds to line 12 is the left picture and not the right picture. if when you call when you call node on line 12, if it's making a copy of the thing that's in B node, then you actually get the picture that's on the right. I'm sorry, on the left. That picture. Yes? Do you see that? That's a possibility. And right now, we don't really have a way of testing and making sure that that is or is not the case. Right? So it seems like what we're trying to say, if the theory that all of you, right, everybody basically drew me the right picture, not the left picture. So all of you seem to think that what happens is the right picture. Yes? So what you're essentially saying is that B tree dot left is the same as B tree dot right. Yep? Yes? That's what you're all claiming. Okay? Yeah, that's true. Good. Did we confirm our theory? No. What should we do to confirm our theory? What else should we do? Check something about A tree. What should we check? Okay, A tree dot left is the same as A tree dot right. Do you want that to pass? Why fail? Because otherwise we haven't told these two apart. So actually what you want is that you want that this is not the same. Right? Because then that would somehow tell us, look, the left and the right are the same, and here the left and the right are not the same. Right? That's a thing you would like to be true. You want them to is not be the same. Yes? Ready? Run it? Yeah? Okay? And no, as a matter of fact, it says, not quite. It failed. In fact, they are the same. Are they the same? Well, so the problem is we now have to ask the question, what is sameness? That's really the question we're trying to ask. Okay? So a different way to put it is, we don't know exactly what's happening in the programming language. I do, but you don't yet. And by the end of this class, you will. But also, we don't have a way of actually asking the questions we want to ask. We don't, like we have this operation is, and is not is presumably the negation of is. So, by the way, there's actually several not operations. So you've seen satisfies, right? So this is not, there's also satisfies not, and so on. And it turns out when you get past is not, it's actually very subtle what the / testing not means. Very interesting question, which I will make sure I don't get distracted into talking about today. So what we don't have is a way of asking a question such that it tells these two trees apart. Right? That's our problem. We don't have a way of asking a question that tells the two trees apart. That's what we need to figure out. Yes?
What happens if we test atree.l is btree.l?
Okay, we can do that. I'm happy to. It's just code. So atree.l is btree.l. Right? That's what you wanted. What do you think this should produce? So let me get rid of this thing here. Okay? In fact, we know that it is, right? So it's passing the is. What should happen for this new test over here? Succeed or fail?
Succeed.
Succeed? Okay. Succeeds. But there's a very real sense in which they kind of are not, right? Yeah?
Can we try making B node mutable and then we can...
No. Next. Yeah.
Do you have a quality operator that checks like the memory address?
Yeah, so we had an operator that tells you the memory address off, and that would be extraordinarily dangerous to give you. Right? If we did that in JavaScript, basically the web would already be crashing more than it already does. So no, we can't do that. So, but that's essentially what we want to know is this making a copy or is this not? Okay? Is this there's two notions of sameness. One notion of sameness is when I print it, does it print out the same? Does it look the same? And the other notion of sameness is it actually truly the very same node that is stored in memory? Those are our two notions of sameness. Okay? And what you can tell from our examples so far is that and this is a good example, the A_L and B_L, what they're testing for is, do they print out the same? Arguably because that's a choice that was made in Pirate, and arguably because that would be the least confusing, right? Because if two things printed out the same and we said, no, they're not the same, you'd be like, what? But I printed them, look. And you think about the error message you would get, right? So let's go back to the is not case over here, okay? And let's print it out and let's look at what it actually says, right? It says it failed because only succeed left and right are not equal. Left side is this and the right side is this, right? And you look at this thing, yeah, okay, they obviously are the same. So it'd be bizarre for me to come back and say they're not the same. So by default, Pirate made a particular choice, okay? So what we need is a different testing operator. And so I'll show it to you now, and it's identical. So identical of A_L, comma A_R is identical of B_L, B_R is, well, so identical is going to behave differently. So identical of A_L, so this is, if this is our correct picture of A tree, and that's our correct picture of B tree, would you expect the left and right of A tree to be identical? And would you expect it of B tree? Okay, what do you expect for this one? Identical of left and right. True. How many? False? Okay. This one, identical of left and right. True? False? Okay, let's give that a try. So what did you all vote for? You voted for false and true, is that right? Mm-hmm. Yep, ready? We ready? 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 Okay? So just in case that did not feel satisfying enough, let's actually just run it over here. Okay? And B tree. Questions about that? Just about what identical seems to be doing? So, we're actually seeing a lot of things here, more things than you may initially realize. So, one thing we're seeing is that we have a new testing operator now. Okay? And that testing operator is identical. So, identical is also a binary operator. It takes two arguments and it returns a Boolean. As you can see, it takes two arguments, returns a Boolean. And it tells you whether the two things are the fruit of the same allocation operation. So when we say B node is node 4, what's happening is we're going to the computer and making some new space. Right? We're allocating a node. Allocating is the fancy term in computer science for making space and putting something in there. And we're writing 4 in there and writing 4 leaf and leaf into that memory space. And that makes a new thing. And identical asks, were these two things made at the same instant in time? Given that only one thing happens at an instant in time, the way to think about it is, are they the fruit of the same instant in time? And if you look at what's happening in A tree, on line 8 and lines 8 and 9, there is a node being created on line 8. There's a node being created on line 9, but those are at two different points in time. There are actually two copies of that node in memory. Even though they look identical, right, they are actually two copies of it. So how many node 4s are in memory at the end of this program? 3. 3 on the left-hand side, actually a few more if you add things on the right, but we haven't done that on the right, okay? So a total of 3 different things in memory, right? 1 on line 8, 1 on line 9, and 1 on line 11. And identical is asking whether these are all the same or not. So let's actually write this other test over here, the A tree, B tree one. Talk to your neighbors and come back and tell me what that should be. Go.
You could make it true like
How many for true? How many for false? Okay, let's try that. Okay? Because they are truly, there are 3 of them in memory, 1, 2, and 3. Okay? And this one and this one are obviously not the same. Question?
So I know like when we're supposed to do like if statements in cases we're not supposed to do like colon and then true. Is there like a better way to do identical than saying is true or is false, or is that how you're supposed to test it?
Yeah, well, so, okay, here, well, there is a better way, so let's look at this. So we could do the following. We could say a tree.l. Let me just write this and then let me rewrite it, okay? So, okay, is that the same as asking identical? Why not? We just demonstrated that it's not, right? So what we want is, we don't want the default, so is has some operation underneath it. Okay? Is a piece of syntax, but underneath there's actually a function being run. It's actually a function called equal always. Okay? And is a nice syntactic shorthand for it in the case of writing tests. So what we'd like is, we'd like to say, I want is, well, I want to write a test case, but I don't want to use equal always as my underlying primitive. Okay? So you can do that like this. Okay? And so what this says is, check for equality, but instead of using equal always, use identical as your primitive. And so this line 9, so what did I do? On over here, this line 22 is the same as line 20, and line 23 is the same as line 19. There's, by the way, another advantage to not writing it in terms of is true and is false. There's a subtle advantage to not writing in terms of is true or is false. Any ideas? Yeah.
You don't have to like store the Boolean in memory, like the false.
No,
like an
it's not
extra.
going to cost. I don't know what cost model you have in mind, but no. Yeah.
If it's raising
If there's an error, one of them will tell you what.
which side it's on.
Well, let's try this. Okay, so let's take this. Let's take line 22, 21. I'm going to copy it and I'm going to make it wrong. So I'll say it's true. Okay? So let's look at the error report. So when we look at the error report, basically the error report says false is not true. Well, yeah, I kind of knew that all along, right? But if I write this in terms of a_tree.l is not identical to b_tree.l. Okay, did I transcribe that correctly? a_tree.l, b_tree.l, and since it's false,
I don't think we'll
okay. So I need to say is, right? Because I want the wrong answer. Okay, and if I say is identical, it's going to come back and say here. The left side is node 4 and the right side is node 4. So it's actually telling you what the real values are instead of just saying true or it's not false. Right? This is the actual useful information. Of course, it's not useful enough because, I mean, they look identical, right? So, yeah. So that's not going to solve that problem for you. So what should you infer from this error message? What should you infer?
So we know that the actual values are the same, so we know that the issue is with this.
Yeah, let's not even say the values are the same. The printed values look the same. Therefore,
That means that it's the memory issue.
it must be something about different allocations. They must have come from different allocations. That's what it means. Okay? Questions so far? Yeah.
If you keep defining variables, will it go down to the base value? So if you were to say c equals b_tree.l, and then
Let's try that. Okay, so c equals b_tree.l. Okay?
And then you were to do an identical, so like on line 21, just replace btree.l with C.
Okay, great. So let me fix this, by the way. Is not, okay? So line 21. Let me write in this other form instead, okay? So you're trying to say btree.l is identical to C?
Or just replace btree.l with C and do,
Well, why don't we try this one?
Okay.
Is that's one of the questions you were asking. Well, we don't know what's same anymore,
Okay.
right? We should write tests to check which one's the same. So you're proposing two tests. You're proposing this one, and you're also proposing, I believe, just saying C is identical to C. Is that the other one you were proposing?
I think I was saying btree.l is identical to C, but both are.
Okay, so I mean so that's what you got right there, right? Okay, ready? Try this out. What do you expect for just so you can see, line 13 has the definition of C. Line 27 says btree.l is identical to C. You expect true? Like you expect this test to pass? Expect the test to fail? Ooh. Ready? Why would you expect this test to fail? Think about why you might expect this test to fail. So the reason you might, well, I don't know why, but I think one of the reasons you might is you expect somewhere some copying is going on, right? That somehow when I make a variable, a copy is going on. Variables don't make copies. Variables are simply, so the way to understand memory is there's a collection of things that are allocated in memory. Okay, so there's a bunch of nodes that are allocated in memory. And there's a separate space, I'm going to give you like the 2-minute version of a compiler's course here, right? So there's details I'm obviously leaving out. There's a separate space where variables live. Think of it as a dictionary if you want, right? A and B and C and whatnot. And these are references to there. So you could have multiple variables that both refer to the same thing. Right? So we could say D equals C. And then we can ask whether D is identical to C. And it's going to come back and say true because, and the fact that it didn't fail means it's true, because what happens with identical, anytime you refer to a variable, you're not referring to this location, you're referring to the location that the variable refers to. And so C resolves to this, D resolves to this, and what you're asking is this thing in memory identical to this thing in memory? And that is the very definition of identicality. Okay? So so the point is when I say D equals C, note that nothing gets copied anywhere. I am using a little bit of extra room to record the fact that D exists. But when I say D in my program, I'm actually getting this object in memory. Okay? D essentially has no existence. The only things that have an existence are the values that sit in memory. Question?
Is that why you can't like change variables? Because then it would have to change what's...
That's a more complicated topic. Change is a really complicated topic, and we'll do that. We'll spend several weeks on that in November. Okay? Like, without understanding this, you're not in a position to even begin to understand change. So until we nail this down completely, we can't begin to talk about change. Yeah?
Are numbers...
Because there's also two kinds of change. You all know this from Java and Python, right? They're two completely unrelated kinds of change. When we say equals, they're completely different things that happen and with the same syntax. That was obvious. No, it wasn't. But that's why we'll do that in more detail later. Yeah.
Are numbers stored as pointers, or are they stored as a variable? Like, if you know what I mean there.
Numbers are irrelevant to this conversation. We can ask the following question. We could ask, is 5 identical to 5?
That would be...
5 is identical to 5. That means there's only one 5 in the world. That's nice to know, right? I mean, well, let me tell you. Okay, this looks goofy. Hold on. If I say node 2 leaf is identical to node 2 leaf, What do you expect that to produce?
False.
So you expect that to not be identical, right? You expect this to pass.
Yes.
Okay, so it is not unreasonable for 5 to not be identical to 5. Every time you say 5, a new 5 gets made in the computer. Right? There's no reason why that could not be true. It is not actually hard for me to conceive of a language or build you a language where that would be true. Where 5 is not identical to 5. Every time you say 5, you get a fresh 5. Okay? There's actually an optimization built in. It's not a very sophisticated one, but it's an optimization built in that says, don't do that! That's insane! We'd have our computer completely littered with copies of 5s and 3s and stuff like that, and we don't want that. So we've chosen to make a decision that even though no two-leaf, we could have also done this, right? We could have said every time you say no two-leaf, we'd say, have you already done that? Well, if you've done that, let's reuse it. Let's not make a new no two-leaf. We could have done that. We chose to make one of these be identical and another of these not be identical. That's a language maker's choice. Yeah?
If you do no two leaf dot L is identical to 2.
Oh, that's a very good one. You mean dot .v, right?
Dot V.
Yeah. Okay. So node to leaf dot v is identical to 2. Pass or fail? How many think it's going to pass? How many think it's going to fail? Okay. Let's confirm it's going to pass. It's going to pass. Better pass. Okay, good. Yeah. Okay. Good. Yes.
Is 5/2 identical to 2.5?
Ooh. Ooh, very nice. Okay, so.
Yeah.
Ready? You have no idea, right?
Yeah.
Okay, good. Yeah.
Is a leaf identical to a leaf?
Ah, much better. Okay. Identical leaf. Okay, ready? Now. Whoa, what happened there? What happened there? So leaf is behaving more like what than like what? It's behaving more like 5 than like node, right? And that's because there is another optimization built into Pirate, which is when you have these kinds of data types, the things that have no parameters, they're constants, right? So it says, look, if we penalized you for that, then you'd be less likely to do that for constants. So for example, if you want to define a traffic light, right? You might say data colors is red or blue or green, right? That's a thing you might want to say. And then you want to use those extensively for building a simulation. Well, if we penalized you for that, if we made that be an allocation for writing down constants, then you're going to be like, oh, that's expensive, so I'll just say a color is 1 equals red, 2 equals blue, 3 equals green, and then you'd say type color equals number, right? And now your program is much worse for that. Right? That would be terrible. That would be a bad penalty to impose on you. And that's why we want to make this, the line 6, 7, 8, just as cheap as the thing that I wrote in a comment. And that's why Pirate does this optimization to say anytime you have things that are essentially constants, because they have no fields, right? So they can't possibly be varying. I will make one of them, and I will reuse that one every single time. So when I said we made a conscious decision to not reuse node to leaf, but made a conscious decision to reuse the 5s, I purposely left one thing unstated, and that was your example, right? We also make a conscious decision to reuse the leaves. Yes?
Would you show us the error message with 5/2?
Oh yeah, absolutely, happily. Sorry, I shouldn't have erased that. Yeah. 5/2 is identical to 2.5, right? Good. Okay. So, yes.
I just don't understand that, because like
Yeah,
if
yeah,
it's like evaluating.
Absolutely. So to actually explain that to you, I would have to explain the full numerical system computational model in Pirate, which I would so love to do, and is so totally not relevant to this course that I'm not going to. I'm going to leave that dangling and unsatisfying. And if you ever take 173, you can ask me that question in 173. Yes.
If you had done 5.
Oh yeah, you go to town. You have a computer after class, you can go to town. Okay, good. Okay, now, what I want to point out is that you've actually learned something important about the computational model of Pirate, which is the same as the computational model of, at a high level, of Python or Java or OCaml or Racket or almost any other language you'll use. Pretty much with the exception of, I mean, I'm excluding things like, SQL or Excel or something, right, which are really quite different. The only other sort of mainstream general purpose language that is different is Haskell or derivatives of Haskell like Agda, okay? So essentially, other than Haskell, I'm giving you the computational model that's true for most of the languages you will program in, or all other than Haskell, right? Which is, when I say node 5 B tree B node, okay? What did we just learn about that expression? What did we learn about that expression? We learned something really important, which is that something does not happen. A copy does not get made. Now, if you've had some prior computer science, you probably have various random terms in your head, call by value, call by reference. It's complete nonsense. Most people don't understand these terms. I'm not going to use them because I'd have to then define the term, and you'll have proactive interference where you've had a previous definition of the term and it'll interfere with the new definition. So I'm just not going to use these terms. Okay? The point is, when you make a call, a copy does not get made. The expression gets evaluated. The act of evaluating B node is going to be one of these things over here. Okay? So it's referring to some node over here. So when you say B node comma B node gets evaluated to this, B node gets evaluated again to this, and those are identical, and so this is the picture that forms in memory. That's what you need to understand. Now, you've actually been assuming this all along. This shouldn't even have been a question, because you have been assuming this all along this semester, starting about 2 weeks in. Talk to your neighbors and figure out why you've been assuming this all along. Go.
What we've been equating objects with data structures. Like we create our own data structures, and they're just obviously Pirate doesn't know how to evaluate some data structures, so they're just doing them friend. It's like when we make our own strings.
In 5, in 4, in 3, in 2, in 1, and we're back. Okay, why have you been assuming this? Anyone? Why have you been assuming this?
You keep on telling us that link is a constant time operation.
Ah, link is a constant time operation. Imagine if that were not true. So let's do this, right? So let's do L is equal to range of some largish list, okay? L1 is link 1 onto L. L2 is link 2 onto L, okay? Now, what checks ought to succeed? You know what I'm just gonna erase this whole thing if you don't mind, so we can actually see errors if we get them, okay? What checks ought to succeed? Yeah.
L1.rest is identical to L.
L1.rest is identical to L. What would that mean? if that test succeeds, that means when link was constructed, when L1, when the, I'm going to say something complicated on purpose. When the value that is bound to L1 was constructed, parse that phrase, read it. When the value that was bound to L1 was constructed. Because the value is separate from its names. You're going to have multiple, the whole point of today's class is you're going to have multiple names referring to the same value. Right? Names and values are not one-to-one. There's a phenomenon called aliasing. And if you ever do parallel programming, this will turn out to be a major nightmare. Because with aliasing, it means there are two different ways to get to the same value. And this is like concurrency problems come about because of aliasing and the presence of side effects, which we'll talk about later. Okay? So aliases, two different names. That's what an alias is, right? If you have an alias, that means you have two different names to respond to. These values respond to two different names. Right? And in this particular case, the names are slightly complicated too, right? One of them is L, the other one is L1.rest. But if this passes, if this test passes, that means it must be the case that, well, it could be that a link copy was being made, but then the copy was being made and thrown away, so kind of pointless, right? The bottom line is L1's rest field is the same value as L. It's not a copy, it's not just a print equal value, it is literally the same value. And so we can also do this, we can also build a little function for ourselves, right? So we'll ask, okay, so we can now run, is it the same? Right? What are we expecting to get? We're expecting to get true, and if you did not get true, that means a copy would be made. Now, of course, you have to trust me a little bit on how identical works. There's actually another thing you can do, right? You could make L be really large, and then you can time how long it takes for link to work. No, seriously. Make L really, really large, and time how long it takes for link to work, right? And at some point, I can assure you that you'd run out of memory on your computer before you can notice a difference, right? Because link is actually taking constant time, effectively constant time. And so it will take the same amount of time no matter how big the size of L. And that also gives you some insight. Okay? But also, if you trust me on the implementation of identical, then is it the same as telling us that when the function is it the same was called, a copy was not made of L. Right? You have, and when I say you've been assuming this for several weeks, you've also been assuming that function calls take constant time. If copying happened, function calls could not possibly take constant time. Our big O complexity for a function call would have to take into account the size of the datum because a copy of that datum needs to be made. And you didn't assume that. So even though you came to class today assuming, some of you assumed that certain copies got made in certain places, that was absolutely not the case for function calls, big O complexity. And link, of course, is then just a special case of a function call. But you might think, oh, it's a built-in function call. And that's why I'm showing you a user-defined function call also has this property. Right? You see why this example is important, that is it the same is proving to you that no copy got made. Yes?
Just really profiling as you're talking about timing, how long it takes. Is there any sort of like warm-up effect that you have in Pirate? Because I know in Java, because of the
Yeah, there's warm-up effects. There's also garbage collection effects. It's real complex. Real timing is complicated. Yeah. Okay. I wanted to show you one other thing. So let me do this. Oh, okay. Two things. So first, I'm going to define. So I'll make a really quick. Right? So if I take one's head, I get a 1. If I ask for one's tail, I get that. And so if I call that, I get that, which looks the same. So I could certainly ask check one's is ones dot t. Expect that to pass or fail? Seems to pass. But the more interesting question is it identical?
I think so.
How many vote for yes? How many vote for no? How many like I have no idea? Okay, good. That's the correct answer perhaps. Okay, it is actually identical. And it's identical because when we took the rest field, we got this lambda. When we called the lambda, it returned ones and no copies were made anywhere. So the structure of ones truly is, there's a node, in this case LZ, 1, with a lambda thing, whatever that looks like, okay? But in there is a reference to ones, but ones got evaluated. Remember, every time you refer to a name, it gets evaluated. So it got evaluated to be a reference back to the same node. So it is truly a infinitely long data structure with a finite, where you can pull out finite prefixes. Okay? Truly is an infinitely large data structure because it's a cyclic datum. Okay? So it's not just a recursive datum, it's a cyclic datum, and that's a distinction. Recursive means has references to the same kind of thing. A binary tree up there is recursive. It has references to the same kind of thing. This is a cyclic datum. It has a reference to the same thing itself, to an identical thing. Okay? And this should also be familiar from homework. Yes? Right? Because you had to deal with the same thing in homework. There's a hand up somewhere. Yeah?
How does it compare to anonymous functions for is?
How what?
How did it compare to?
Oh, I don't want to get into that. Okay. So, long conversation. Not germane to the point I'm trying to make. Now, the last thing I want to point out is, we started today with a copy tree. Does our copy tree actually make faithful copies of trees? Is there a sense in which our copy tree does not make faithful copies? Can you write me a test case that would illustrate that point if you think that's the case? So let's say I say,
She is identical to.
one would hope that T dot L is identical to T dot R. Right? Why not?
Isn't that like the exact opposite of the definition of a copy? Is that they're not identical, but they have...
No. I didn't say T is identical to B. I didn't say T is identical to B. I said B is left and right are identical. So I would expect T's left and right to also be identical. That would be very much the definition of a copy, right? And of course that isn't going to succeed. I mean, it prints the same, but this is our problem. They print the same, but they're actually different nodes. Yeah?
And why would you think it's the same? Because in copy, even with left and right, you're asking for two different copies.
So, the question is really, what if I wanted them to be the same? So imagine this, right? You have a backup system. You have a disk backup system. What actually happened is, we started with a 2-node tree, and our copy turned it into a 3-node tree. So if you had a disk where you had one directory that had two subdirectories that pointed to the same thing, that means your backup has now blown it up into a 3-directory file system. You wouldn't be happy with that. You'd be pretty unhappy. In fact, every time you make copies, you might potentially make things worse, right? So this is called a tree. This structure is not really a tree. It's got its own name in computer science. It's a really cool concept. It's called a directed acyclic graph. for reasons that'll become clearer as we go along, but it's a directed acyclic graph. It's a graph, which means it could have cycles, except it's acyclic, which means it doesn't have cycles. Okay? But it's a richer data structure than a tree because it has sharing. Trees, by definition, literally the math definition of a tree is there's no sharing. Okay? So this is a DAG, and that's a tree. And so it's an interesting question to ask. Can you write a copy DAG that preserves the DAGness? Yeah. Okay? Think about that for homework. Go.